Okay, today we're going to take a look at the beginning of Chapter 8. Chapter 8 is called the Binomial and Geometric Distributions, and we're going to start with our first half of 8.1, which is just focusing on the binomial distribution. Now, the first thing we have to do is gain an understanding of what that means to be a binomial distribution, and then we'll start to talk about the probabilities associated with that distribution. And this is kind of picking off of where we were in last chapter when we were talking about a random variables, discrete and continuous. This is just another situation that could be modeled using probability. Oftentimes we look at random phenomena where there are two outcomes of interest. You have a football game, and before the game there's a coin toss. And, well, you could either be a heads or a tails. A basketball player shoots a free throw. They either make it or they miss it. A young couple prepares for their first child. Maybe it's a boy, maybe it's a girl. There's two outcomes, okay? Generally, considering the situation, we'll consider one of them a success and the other one a failure. Now, that doesn't necessarily mean that one outcome is better than the other, but for the purposes of these problems, we're going to just use that vocabulary, success versus failure. Let's look more into this idea of free throw shooting. Let's say Gretchen is a 60% free throw shooter. That means that she'll make 60 out of every 100 on average of her free throws. In one particular season, she shoots an average of 75 free throws. If we wanted to find the probability that Gretchen makes exactly 50 out of 75 free throws, or if we're looking for the probability that she makes more than 50 free throws, or no more than 40 free throws, all of those are examples of binomial distributions, and we would find the binomial probability based on what we're going to learn here in this section today. Because shooting free throws is something that we refer to as a binomial distribution. Partially, but not completely, based on the idea that there's two outcomes that are possible, make or miss. So what is a binomial distribution? Well, we still have this random variable x that we're referring to, but in this case, x is going to be the number of successes. So she's shooting 75. What's the probability that she makes 60? That would be the probability that x equals 60. We call x a binomial random variable. Excuse me. So it's random, as we talked about back in Chapter 7, but it has a specific distribution, which we refer to as binomial. Now, in this situation, it's actually a specific kind of random variable. It's a discrete random variable. As you'll see, we'll be able to write these out in probability distributions. But, it's a little bit different at the same time. Now, our notation, we are used to writing notation that looks like this, where we say n parentheses mu comma sigma, where we have a normal distribution with mean mu and standard deviation sigma. Now, in this section, we have some new notation to talk about, and it's b parentheses n comma p, where the capital B just tells us that it is a binomial distribution, and it's the number of observations, and p is the probability of success for any one of those observations. Now, the number of observations, if we're talking about Gretchen and her shooting free throws, if she shoots 75 for the season, then 75 is our observations, okay? If we're looking for the probability of success, well, then that's a situation where she makes 60% of them, so the p would be 0.6. Obviously, x can take on any whole number value from 0 to n. Now, before we can get into finding what those probabilities are, we need to clearly understand the four conditions that are needed to be determining whether a distribution is binomial or not. The first one is the one we've been talking about. Each observation falls into one of two categories. You either have a success or a failure. There's a fixed number of n observations, meaning it's exactly shooting 75 free throws, or you're tossing a coin exactly 6 times. The n observations are independent, meaning the outcome of one of them has no impact on the outcome of another one. Therefore, the probabilities, as we stated before, the probability is constant. It's the same for each observation. Okay. Now, the one that might hang some people up is the first one, success and failure. If we're rolling a dice and we want to see how often we're going to get a 3? Well, in that particular situation, a success would be rolling a 3. And a failure, well, is anything other than a 3. So it could be a 1 or a 2 or 4, a 5, or a 6. We're not saying that the probability of success and the probability of failure has to be the same. Clearly, in this case, it's not. The probability of success in this case would be just 1/6. The probability of failure would be 5/6. So just because we have two different kinds of outcomes doesn't mean there are only two outcomes, in fact, that we're measuring. It's not just a made shot or a missed shot. There are different ways to measure success and failure. So let's look at a few examples and determine if we can figure out if these distributions are in fact binomial or not. Person here says blood type is inherited. If both parents carry genes for O and A blood types, each child has a probability of 0.25 of getting two O genes and the same of having blood type O. Because if you have two O genes, then you have blood type O. A success is the child getting blood type O among the 5 children of these parents. So the first thing we want to consider is, well, do they have a success and failure? Well, in this case, we are told that a success is the child getting blood type O. So if that's a success, then any other outcome is going to be a failure. And in this case, since the parents only have O and A, well, they could only be either O or A. So yes, they're either type O or they're not. So there's success and there's failure. The second condition is to check if we have a fixed number of observations. And in this case, we have 5 children. That's a fixed number. Those number of children they're having is not going to change. They're only going to have 5. So it's a fixed number of observations that we're considering. We want to know, are these trials independent? Well, it says each child has a probability of 0.25. It's not changing. It doesn't change. If the first one has blood type O, it doesn't mean that the second one is less likely to have blood type O. So yes, the child is independent. And if they're independent, then that means that the probability will be constant. You'll see that basically 3 and 4 go together. If they're independent, the probabilities will be the same. That's pretty much what the definition of independence is, but we list them out as separate conditions anyway. So therefore, this is a binomial distribution, and we say that the n is 5, and the probability of success is 0.25, just to kind of keep that notation in mind. Take a look at the second one here, and you should probably pause at this point and try to determine if you can figure out if this one is or is not binomial. It says you deal 10 cards from a shuffled deck, and you count the number X of red cards. A success is a red card. So again, they're telling us what it means to be a success. So it's either a red card or it's not a red card. And that's really all that matters. So we have success and we have failure. Okay. However, what's happening with this particular situation is that these 10 cards are being dealt. If the first card is a red card, then that changes the probability of the next card. You're less likely to have a red card second if the first one was a red. So while it does have a success and failure, we do have a fixed number of observations. The condition of independence is not upheld, and therefore condition 4, the probability is not constant throughout either. So this is an example that is not binomial. Let's look at one more example here, binomial or not. And again, I would pause it, take a look at it yourself, see if you can determine whether it's binomial. An engineer chooses an SRS of a random sample of 10 switches. That's kind of important. From a shipment of 10,000 switches. Suppose that, unknown to the engineer, 10% of the switches are bad. The engineer counts the number X of bad switches, so that's what we're looking for. And this is kind of weird, because what we're looking for is our success is a bad switch. So this is an example where success doesn't mean that it's a good thing. In this case, finding a bad switch is considered a success. So that means if you find a good switch, well, that's a failure for this particular situation. Success and failure don't have the same definitions as they do in a traditional setting here. But we do have this idea of success and failure. It's either a bad switch or it's not a bad switch. Do we have a fixed number of observations? Yes, we do. We're selecting 10 of them. The tricky part is independence. Now, this isn't like the previous example where there are only 52 cards in a deck, because if we take one of those red ones away, the probability changes not necessarily hugely, but it does change by a measurable amount. In this particular case, if the first switch that I look at is bad, and that is what we consider a success, well, 10% of the shipment are bad. If I take 10%, that's 1,000 out of 10,000. Well, now, the first one was bad. So now there are only 999 out of, whoops, I lost the zero there. Out of 9,999. And are those probabilities the same? Well, not exactly. But they're pretty close. They're pretty close. But if we were to say that this is truly a binomial distribution, well, no, it's not, because these two probabilities are not exactly equal to each other. So in this particular case, it's not quite binomial, because the independence principle is not strictly upheld, and therefore the probabilities are going to be slightly different. But as it says down here, sometimes it will be okay to consider it approximately binomial for purposes of estimation. Now, that is going to sound ambiguous to you. It's going to sound vague, because then we have to say, well, okay, well, how large is large enough for us to be able to consider it approximately binomial? And our rule of thumb is that if our sample is less than 10% of the population, you can't really see that, the decimal into the inequality. If the sample is less than 10% of the population, then it's okay to assume independent. Okay? And in this particular case, our sample is 10, our population is 10,000. Clearly, 10 is less than 10,000, so this would be okay to consider it as independent. Okay? Assuming that, and this is continuing the previous example, assuming that a defective switch is drawn first, meaning the probability of that is 0.1 or 10%, the probability of the second switch being defective changes to 0.0999, because, as we showed, it's now 999 bad switches out of 9,999. And it says, for practical purposes, this is close enough, and therefore it behaves like a binomial setting, even if the condition is not strictly upheld. Okay? So, again, for now, we're just going to say if it doesn't change significantly, then we can say it's approximately independent. Eventually, we're going to use that rule that I showed on the previous slide, where the population has to be at least 10 times the sample size, or the sample must be less than 10 times the population size. You can say it either way. When the population is much larger than the sample, a count of successes in an SRS size and has approximately the binomial distribution. Okay, so if I can tell you that, again, the population is at least 10 times the sample size, we're okay. All right, now we are understanding whether these distributions are binomial or not. Now let's talk about actually finding what the probability of success is. And before we can get into the actual probability, we have to understand a little bit about probability. And this is something that you've seen before in Algebra 2. It's considered the binomial coefficient. And what it's basically saying is, well, if we have, let's say we're shooting 5 free throws. And with those free throws, we want the probability that x equals 3. In other words, that we make 3 free throws. Well, maybe we make the first 3, and we miss the second of the 2 at the end, excuse me. That would be a situation that shows that we made 3 out of the 5. But it doesn't have to be that way. Maybe we miss the first 2 and we make the last 3. Again, that's the same situation as finding out that you made 3 out of 5. And I could write this out a lot of different ways. Making 3 free throws out of 5. How many different ways there are to write that out is what we refer to as the binomial coefficient. It says the binomial coefficient is the number of ways of arranging k successes among n observations. And the notation that you're probably familiar with is right here. And it looks like a big parentheses. It's not actually parentheses, it's just the way that we notate our binomial coefficient here. And it's just n over k. We read it as, for n observations, how many different ways can we arrange k successes? And this probably looks at least a little bit familiar, where we have n factorial over k factorial times n minus k factorial. Now, what that means is when you have n factorial, let's just say, going to our example up here, if we were looking to do 5, choose 3, using the vocabulary you're used to from Algebra 2, we would take 5 factorial over 3 factorial times n minus k factorial, so 5 minus 3 factorial. Now 5 factorial is 5 times 4 times 3 times 2 times 1. So 5 times 4 is 20, times 3 is 60, times 2 is 120, times 1, well, that doesn't matter. Over 3 factorial, that's 3 times 2 times 1, so that's 6, times 5 minus 3 factorial, well, that's 2 factorial, 2 times 1 is just 2. So now I have 120 over 12, that's just 10. Telling me that there are 10 different ways that I could arrange these 3 successes among 5 free throws. Now for this example we have here, it's not too hard to write it out in those 10 different ways. But as we saw back in Chapter 7, sometimes we mess up, sometimes we forget one. Okay? Now the good news for us is that we don't have to use this formula, although it is on the formula sheet. We can use the graphing calculator, or actually it's not even necessarily on a graphing calculator, it's also on a scientific calculator, using the NCR function. NCR function. And if you hit on your graphing calculator, math, and cursor over to probability, you'll see that NCR function again. Where you hit, in this case, you would hit 5, then you would hit the NCR button, and then you would hit 3. And if you hit enter, you should see that you get 10. And I would take a moment there, and I would prove that in your calculator, pause the video, and then hit play again when you prove that that happens. Now, keep in mind, this is not actually finding the probability. This is just determining the number of ways that you can have these number of successes in these n trials. Then once we have that, then we look at actually finding the binomial probability, or the probability of success in these situations. And it's going to start with that binomial coefficient, right? Coefficient, we're multiplying it by something else. And what's actually going on? Well, we're going to start with that binomial coefficient right there. And again, this is the probability that x equals k. In other words, we have k successes. Just notation why we use k. Doesn't really have to be k, could be anything there. It's just awkward to say that we're going to have x successes, because then you have 2 x's, although one's uppercase, one's lowercase, whatever. So anyway, the formula says n choose k. The next part of the formula, if we look right here, it says p to the k. What does that mean in words? Well, p is the probability of success and we're raising that to the k, which is the number of successes. So that's just like if you had 2 made free throws, you're going to multiply 0.6 times 0.6, because it's 0.6 squared. Well, that makes sense. And the next part here says 1 minus p. Well, if p is the probability of success, then 1 minus p is the probability of failure. And if k is the number of successes, well then n minus k is the number of failures. Sorry, it's a little crumpled there in the corner there, but trust me, it says the number of failures. So we have the number of ways that you can have these successes times the probability of success to the number of successes times the probability of failure to the number of failures. In my experience, understanding what the formula means makes a lot more sense, and therefore I can use it a lot easier than if it's a situation where I'm trying to memorize a formula. Okay. Quick note, some books, and if you are looking around the web and things like that, some books will say instead of 1 minus p, they'll use just the letter q to represent the probability of failure. Okay. I'd rather not have to introduce another variable there, so I'm going to keep the 1 minus p to represent the probability of failure, because those are the only two possible outcomes here. Alright, so let's put this formula to use for an example or two. It says recall that the probability of a child being born to a particular set of parents has the probability of 0.25 of having blood type O. If these parents have 5 children, what's the probability that exactly 2 of the 5 have blood type O? Well, we've already proven that this is a binomial distribution with n equaling 5, and the probability of success was 0.25. Okay, so now we can go ahead and figure this out. The first thing we want to do is we want to do 5 choose 2. 5 choose 2, and again, whether you do it in your calculator or if you go ahead and do the formula for it, which would be 5 factorial over 2 factorial times 5 minus 2 factorial. By the way, this should look familiar because it's pretty much the same thing we did before, except now the 3 is going to be underneath there, and now the 2 is there. But it should still turn out to be 10, as we found in the previous slide there. That's the binomial coefficient. And then we see probability of success to the number of successes, that's 2. Probability of failure to the number of failures, that's 3. And then we just go ahead and figure it out. 10 times 0.25 squared times 0.75 squared gives us 0.2637. So we say, putting it all together, the probability that x equals 2, in other words, the probability that 2 of the 5 children are blood type O, is 0.2637. Pause it, make sure it makes sense, and then go on. Let's talk about the switch example. All right, so we talked about this. We said it's approximately normal. All right, we know that n is 10 and p is 0.1. We want the probability that no more than 1. Well, if no more than 1 is what we're talking about there, well, that means that we could be talking about x equals 0, or we could be talking about the probability that x equals 1. And since these would be disjoint, all we have to do is come in and add them together. Okay? Now, writing them out each one separately, we have 10 choose 0. Now, if you think about what that means, you have 10 opportunities, and of those, 0 are successes. So you have failure, failure, failure. They're all failures. There's only one different way that you could write that out. You still write it out as the probability of success to number of successes, but since your exponent is a 0, anything to the 0 power is 1, you remember that from algebra, and you're essentially saying that you have the probability of failure of 0.9, and you have 10 of those. So this should be pretty easy. It's really just going to be that's 1 and that's 1, so you really just have 0.9 to the 10. As far as the second part where x equals 1, you have 10 choose 1. Well, that means that you could have a success and then 9 failures, or you could have a failure, the second one is a success, and the rest are failures. That check, that success, could occur in any one of the 10 spots. So that tells you that 10 choose 1 is 10, times 0.1 to the first, times 0.9 to the ninth, ends up giving us there 0.7361. Okay? And again, that's telling us that the probability that x is less than or equal to 1 is 0.7361. And the reason for that, why is that such a high probability? Well, because the probability of success is only 0.1. So, of those 10, you wouldn't expect to have a lot of them be bad switches. All right. The mailing list of an agency that markets scuba diving trips to the Florida Keys contains 70% male and 30% females. I'm glad they told us the 30% females because, hey, how else would I know what else is going on here? The agency calls 30 people chosen at random, 30 people, fixed number of observations. We want the probability that 20 of the 30 are men. 20 of the 30 are men. Okay, so what is this one asking? It's asking for the probability that X equals 20. Now, we hadn't seen this one before, so we should probably consider whether this is or is not a binomial distribution. Well, do we have a situation where it's success and failure? In this case, yes. Success is that you select a man. We have a fixed number of observations. We're choosing 30 people. We know that 70% are males and 30% are females, and we would say that the mailing list has to be large enough to assume that independence can be approximately upheld, and therefore the probabilities will be the same. Okay? Now, if we're trying to figure this out, we say that X is binomial with our N is 30 and our probability of success of 0.7. We want to say the probability that X equals 20. So it's 30 choose 20. Probability of success is 0.7 to the 20th because you have 20 successes. Therefore, the probability of failure is 0.3. And if you have 20 successes, then you have 10 failures because, again, it's out of 30. 30 choose 20 is a very large number, but it's going to be balanced out because we're doing 0.7 to the 20th and 0.3 to the 10th. Those two decimals are going to end up being pretty small, which is going to bring our probability down, and in fact it's 0.1416. 0.1416. In other words, 14% of the time will exactly 20 of the 30 be men. Okay? The second part of this problem, part B, says, what's the probability that the first 4 women, I should say women, that the first, oh no, it's just kidding. What's the probability that the first woman reached on the 4th call? That means that the first 4 calls were male, 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 female. Now, look at this example here. It's a little bit different than the way question A was written. And in fact, this is not a binomial distribution, but this is something that we need to be considering. Why is it not binomial? Well, because we're specifically telling you the order in which these outcomes are occurring. So the binomial coefficient in this case is 1 because there's only one way that we can write this out. All right? So what are we having? We're saying it's male, 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 female. So in this case, we do probability of male, 0.7, to the 3rd because there are 3 of them, and then the probability of female to the 1st because there's only one female. Multiply that out, and you get 0.1029. Again, the only thing that's different about B is that since the order is fixed, we don't multiply by the binomial coefficient as we did in the first example, because there's only one way that this happens. Okay, tomorrow in class we're going to take a look at these exercises here. 1 through 6 on page 516 are just looking at determining whether a situation is binomial or not. And 7 through 11 here, they are actually finding the probabilities for the binomial distributions. Okay, kind of lengthy lesson today, but hopefully you were able to keep up with what was going on, and I will see you guys in class tomorrow.